Hello, good day everyone. I am Lara Imovilia and I will be presenting to you
The history of calculus. Let's start by defining what is calculus. Calculus is one of the most important branches of mathematics that deals with continuous change. It is a part of the history of mathematics that focuses on limits, functions, derivatives, integrals, and infinite series. The subject, known historically as infinitesimal calculus, constitutes a major part of modern mathematics education. Broadly speaking, we can say that calculus began in ancient times with the Greeks who tackled different mathematical problems. In particular, they were interested in solving two classic problems. One was the calculation of areas, and the other was the drawing of tangents. There were several Hellenic characters who made great contributions in this regard. Among them, the most famous was Archimedes of Syracuse, whose work is considered the culmination of the contributions of the Greeks. It was not until the first half of the 17th century when interest in these problems was renewed. The several mathematicians from different parts of Europe, such as Bonaventura Cavalieri, John Wallis, Pierre de Fermat, Gilles de Roberval, and Isaac Barrow, made advances that paved the way for the work of Leibniz and Newton. While some ideas of calculus were developed early in Greek, Chinese, Indian, Islamic, and Japanese mathematics, the invention and modern use of calculus began in Europe during the 17th century when Isaac Newton and Gottfried Leibniz built on the work of ancient mathematicians the basic principles of this discipline. The development of the calculation was constituted based on the concepts of instantaneous movement and the area under the curves. As I was saying, calculus was developed in the latter half of the 17th century by two mathematicians, Gottfried Leibniz and Isaac Newton. Let's learn more about them. Gottfried Leibniz is a German mathematician who developed the present-day notation for the differential and integral calculus, though he never thought of the derivative as a limit. His philosophy is also important, and he invented an early calculating machine. Isaac Newton, on the other hand, is the greatest English mathematician of his generation. He laid the foundation for differential and integral calculus. His work on optics and gravitation made him one of the greatest scientists the world has known. Newton first developed calculus and applied it directly to the understanding of physical systems. Independently, Leibniz developed the notations used in calculus. Put simply, while basic math uses operations such as plus, minus, times, and division, calculus uses operations that employ functions and integrals to calculate rates of change. Those tools allowed Newton, Leibniz, and other mathematicians who followed to calculate things like the exact slope of a curve at any point. The story of mathematics explains the importance of Newton's fundamental theorem of the calculus. Unlike the static geometry of the Greeks, calculus allowed mathematicians and engineers to make sense of the motion and dynamic change in the changing world around us, such as the orbits of planets, the motions of fluids, and etc. Using calculus, scientists, astronomers, physicists, mathematicians, and chemists could now chart the orbit of the planets and stars, as well as the path of electrons and protons at the atomic level. There are two branches of calculus: the differential and integral calculus. For differential calculus, it determines the rate of change of a quantity. It examines the rates of change of slopes and curves. This branch is concerned with the study of the rate of change of functions with respect to their variables, especially through the use of derivatives and differentials. The derivative is the slope of a line on a graph. You find the slope of a line by calculating the rise over the run. For integral calculus, it seeks to find the quantity where the rate of change is known. This branch focuses on such concepts as slopes of tangent lines and velocities. It concerns itself with the space or area under the curve. Integral calculus is used to figure the total size or value, such as lengths, areas, and volumes. Calculus played an integral role in the development of navigation in the 17th and 18th century because it allowed sailors to use the position of the moon to accurately determine the local time. To chart their position at sea, navigators needed to be able to measure both time and angles with accuracy. Before the development of calculus, ship navigators and captains could do neither. Calculus, both derivative and integral, helped to improve the understanding of this important concept in terms of the curve of the Earth, the distance ships had to travel around a curve to get to a specific location, and even the alignment of the Earth, seas, and ships in relation to the stars. Calculus has many practical applications in real life. Some of the concepts that use calculus include motion, electricity, heat, light, harmonics, acoustics, and astronomy. Calculus is used in geography, computer vision, such as for autonomous driving of cars, photography, artificial intelligence, robotics, video games, and even movies. Calculus is also used to calculate the rates of radioactive decay in chemistry, and even to predict birth and death rates, as well as in the study of gravity and planetary motion, fluid flow, ship design, geometric curves, and bridge engineering. In physics, for example, calculus is used to help define, explain, and calculate motion, electricity, heat, light, harmonics, acoustics, astronomy, and dynamics. Einstein's theory of relativity relies on calculus, a field of mathematics that also helps economists predict how much profit a company or industry can make. And in shipbuilding, calculus has been used for many years to determine both the curve of the hull of the ship, using differential calculus, as well as the area under the hull, using integral calculus, and even in the general design of the ships. In addition, calculus is used to check answers for different mathematical disciplines such as statistics, analytical geometry, and algebra. Calculus in economics. Economists use calculus to predict supply, demand, and maximum potential profits. Supply and demand are, after all, essentially charted on a curve, and an ever-changing curve at that. Economists use calculus to determine the price elasticity of demand. They refer to the ever-changing supply and demand curve as elastic and the actions of the curve as elasticity. To calculate an exact measure of elasticity at a particular point on a supply or demand curve, you need to think about infinitesimally small changes in price and as a result incorporate mathematical derivatives into your elasticity formulas. Calculus allows you to determine specific points on that ever-changing supply and demand curve. Here are the important mathematicians in the field of calculus. First, we have Archimedes of Syracuse, the greatest mathematician of his age. His contributions in geometry revolutionized the subject, and his methods anticipated the integral calculus. He was a practical man who invented a wide variety of machines, including pulleys and the Archimedean screw pumping device. Second, Bonaventura Francesco Cavalieri, an Italian mathematician who developed a method of indivisibles which became a factor in the development of the integral calculus. Third, we have John Wallis, an English mathematician who built on Cavalieri's method of indivisibles to devise a method of interpolation. Using Kepler's concept of continuity, he discovered methods to evaluate integrals. Third, Pierre de Fermat, a French lawyer and government official most remembered for his work in number theory, in particular for Fermat's last theorem. He is also important in the foundation of the calculus. Fourth, Gilles Persson de Roberval, a French scientist who developed powerful methods in the early study of integration. Lastly, Isaac Barrow, an English mathematician who developed a method of determining tangents that closely approached the methods of calculus, and he was first to recognize that integration and differentiation are inverse operations.
Thank you for listening. I hope you have learned something from our topic today. Bye!